Thank you. Good morning, everybody, and thanks to the organizers for this invitation. So today I will talk about low-rank approximation techniques and their application to problems for solving stochastic and parametric equations, mainly with a focus on application in uncertainty quantification. I will present you the framework in which I started, in fact, these developments on low-rank approximations. And also I will try to convince you with the subspace point of view in these low-rank approximations that in fact low-rank approximation is closely related to optimal model reduction. More precisely, optimal projection-based model order reduction. So the main context for me, the main application I have in mind is the solution of stochastic or parametric equations, which are typically given by a set of parametrized equations, parametrized by a set of random variables, or simply parameters, that I denoted here xi. So these equations can be ODEs, PDEs, and typically the random variables here are coefficients of your differential operators or random variables that discretize, for example, a random field, which is a parameter of your differential equation. Typically, you have two problems for this kind of analysis. First, the forward problems, where you are given a probability measure for your random variables, and you try to compute variables of interest that are typically given by functions of your solutions, of your model. And then you want to estimate quantities of interest, like statistical moments, probability of events, like the probability of exceeding a certain threshold, or sensitivity indices, for example. And also another and more challenging issue is the problem of optimization or inverse problems, where given some observations on your output, you try to infer the value of the parameters, or even more challenging, the probability measure of your random parameters. So these are the typical questions you may be interested in uncertainty quantification. And for addressing these issues, an ideal approach is to build what we call a meta-model, or surrogate model, or reduced order model, depending on the communities. There are different names. But this is, in fact, in terms of, for an analyst, it's an approximation of the map that associates to the input xi, the variable xi, the solution of your model. Okay? So you want to approximate this map, and in order to have cheap evaluations a posteriori of this solution for many values of your input parameters, and in order to estimate observables, objective function, etc., depending on the context. So this is an ideal approach. This surrogate model or meta-model can be used directly to estimate your quantities of interest, or also it can be used, for example, in Monte Carlo simulation as a variance prediction technique, as a control variate. It is typically used like this, okay, to accelerate the convergence of Monte Carlo simulations. So the main issues in this approximation, first is that you have to manipulate usually very complex models. So even for one sample of the input parameters here, you have a very, very complex simulation to perform, okay? Maybe hours, days of computation for only one single realization of the input variables. The other issue is that here, typically, you will have 10, hundreds random variables that describe the uncertainties in your model. And so you have to face the problem of approximating multivariate function in very high dimension. Even in infinite dimension, it can be the case, and I will come back this later on an illustration. So in order to fix the ideas, I take a very simple model examples, which is a diffusion equation where the uncertainties are on the diffusion coefficient here. So the uncertainty can be given under this form. For example, here you have a typical example in the MOMAS group. It was a benchmark called Couplex, okay, where here the uncertainties was the diffusion coefficient in the different geological layers, and the probability law for these diffusion coefficients, which is constant per layer, was given by physicists, by geologists, in fact, was log normal, log uniform, in fact, random variables here in this benchmark. So here you have a very simple example from a stochastic point of view, because you have only 4 random variables to discretize your uncertainties, and the random field is given like this. Here the main issue is that to simulate this problem you have to, here it's simple 2D illustration, but if you want to have accurate computation here, you have to compute 3D model, okay, with very fine discretizations. The scales are not the good ones here, so really there is an issue even in deterministic computation for this application. So the problem is the complexity of the model here. When you introduce spatially correlated random fields, usually you will discretize this random field and express this random field as a function of basic random variables. And here the issue is the dimension, the stochastic dimension, the number of random variables that describe this random field. And even if you don't want to introduce any approximation of this random field, you are even interested in the case where d is equal to infinite. That means you will have a function of an infinite number of random variable xi. Okay, so first issue, and I want to give you some insight about this issue of high-dimensional approximation. We are facing the problem of approximating a multivariate function. So to approximate this, a naive approach would be to introduce a unidimensional approximation basis, univariate basis, like polynomial basis, which is typically the case in uncertainty quantification, where people use polynomial chaos expansions. They use unidimensional polynomial basis here. They tensorize the basis, and you combine, okay, all these tensorized bases to approximate your function. The number of parameters in this type of approximation is n, where n is the dimension in each the number of basis function in each dimension, n to the power d, the number of variables in your problem. And so, even if you assume that your solution is S-time continuously differentiable, you know that to achieve an accuracy epsilon, you will need a number of parameters that will grow exponentially with the dimension d. And this is what we call the curse of dimensionality. And you may ask, in fact, does extra smoothness help in this problem? Okay, because here I assume CS. And there is a very nice result where, in fact, if you consider this set of functions, it's the set of infinitely many times differentiable functions with uniformly bounded derivatives. Okay, so it seems to be a very nice set of functions. Okay, any derivative is bounded by a given constant. Okay, and you can, in fact, try to measure this quantity, which is, in fact, the error you can obtain by an ideal algorithm. I do not specify what is this algorithm, but I just say that this algorithm will use linear information on the function. For example, point evaluation of the function, integral of the function time a given function, etc. Okay? A linear information, a linear application in your function. And you define this epsilon, which is the infimum over any possible algorithm that use this information, any information on your function, infimum of the supremum, okay, the worst case error, in fact, the supremum over this class of function of the distance between you and the approximation, which is provided by your algorithm. Okay? So the nice result, it seems to be nice, because you have this very nice set of functions. You see that the precision, asymptotically, do not see the dimension. And you have this property for arbitrarily large S. Okay, it seems quite natural, because you are infinitely many times differentiable. But in fact, there is something hidden in the constant, and it was not it was not studied in the literature. In fact, before this paper that you can see in 2009, where in fact, when you look at the constant, you realize that the number of information you need to achieve a precision epsilon grows exponentially with the dimension, even for this set of functions. So what is the conclusion here is that smoothness, or more precisely isotropic smoothness, cannot help in approximating high-dimensional functions. So the remedy for this is to use structured approximation, and it's quite well known in different communities, like in statistical learning, that you have to try to find structure in your function in order to break the curse of dimensionality. So there are different structures that you can exploit and that are exploited in practice, like low effective dimensionality, where in fact your function seems to depend on many variables, but in practice it depends on several ones only. And so you will have to detect this low effective dimensionality. Low order interactions, where basically you try to approximate your function by a sum of low dimensional functions. So it's a typical structure of approximation that is used in practice. Also, a structure that is very widely used in uncertainty quantification is the notion of sparsity, relatively to a basis or a frame. Usually a polynomial basis. There are many results about this. When you can expect to have a good approximation of your function on a polynomial basis by retaining only a small number of significant coefficients in this polynomial expansion. And this sparsity result typically use the anisotropy of the function, okay, in order to break the curse of dimensionality. And in this talk, I will mainly focus on Lowrank structures that I will precise just after. And in some way, Lowrank structure, and I will try to convince you, incorporate different heights, different structures that are here. Okay, it's a kind of generalization of this kind of structures, but I will have to define what is the notion of rank in order to convince you that in fact these functions are low rank in some sense. Okay. Here's something I will not talk about. It's that, in fact, all these structures in practice can be discovered after suitable reparametrization of your problem. So it's another challenging issue, how to find the maps in your parameter space such that you can discover these structures in your function. So I will first present you in a quite general setting the notion of rank and rank structured approximation for high-dimensional functions. And then I will adopt this subspace point of view and try to show you the link between subspace-based model reduction and these low-rank approximation techniques. So first, just one slide, which may be standard for you, but it's a definition of a tensor space. And in fact, you will see later that I will need to specify a little bit what is the structure, the topological structure of this tensor space in order to have some result on low-rank approximation. Because in this form, it's a definition of tensor space, a tensor product of many spaces, okay, not only two. And in the literature, you mainly find books on tensor spaces that focus on the case of two spaces. And in this case of two spaces, the tensor analysis is closely related to the analysis of operators, okay? Operators from one space to the other, okay? Bilinear application or operators. You have an identification. And in fact, the analysis, functional analysis of tensor spaces is quite recent. I would say functional analysis and numerical analysis in the case of higher order tensor space like this. And I recommend you the book of Wolfgang Hackbusch on this topic, which is a quite recent book. It was in 2009. Okay. And it's a quite complete analysis, functional analysis on these tensor spaces. So the basic definition is you are given D vector spaces, and you define the algebraic tensor space, the tensor product space of these spaces, as a set of elements that can be written as a finite sum of elementary tensor products of vectors in these different spaces. Okay, V1i is in V1, Vid is in Vd, etc. If you want to look at this as multivariate functions, elements of this algebraic tensor space are multivariate functions that can be written as a finite sum of product of univariate functions. Okay, and then you define a tensor Banach spaces by the completion of this algebraic tensor space with respect to a certain norm. Okay, this is the general definition of a tensor space. And in fact, these tensor spaces appears in many contexts in stochastic analysis. First, the first problem I mentioned in the beginning of my talk was stochastic or parametric equations, where you have parameters, random parameters with a certain probability measure. Here the big C in the rest of my talk will denote the support of this measure of the parameters. And under suitable regularity assumption on your problem here, your solution will live in a Bochner space, the space of LP function defined on the parameter space with value in some function space V. And in fact, this space is a tensor product space. Okay? You can find it in classical textbooks on tensor spaces, the identification between these two spaces. So the tensor product of the space V and the LP space. Then if you consider multivariate function of D random variables which are independent, then you have a product measure, okay, a product probability measure that gives a tensor product structure to this LP space. So here you will have to deal with higher order tensors to approximate this function. Also, just one slide, and it will not be the illustration I will show you later, but about stochastic differential equations, also you have tensors in this kind of application. First, you know that the probability density function of the solution of this stochastic differential equation satisfy n-dimensional PDE, and the solution is an element of a Sobolev space, which is a tensor product space. Okay, so more precisely, I do not go into the detail, but it can be seen as an intersection of standard tensor spaces. Okay, so this is a particular situation where you have tensors here, and also another point of view, which was in fact the basic, the starting point of polynomial chaos methods in uncertainty quantification, is the discretization of the Wiener process. If you introduce a Karinahan-Love decomposition of your Wiener process, so you express your Wiener process in terms of independent Gaussian random variables, and you can see the solution of this equation as a function of these Gaussian random variables. And if it is an L2 function, okay, L2 function, then you have this tensor product structure for the solution of this stochastic differential equation. And it's the basic point, in fact, of polynomial chaos expansions for the solution of stochastic differential equations. So now, what is Lowrank approximation? It's simply, okay, my function, my multivariate function, I will try to approximate it by a Lowrank function, okay, an element in this set of function with a rank bounded by R. For other two tensors, there is a unique definition of the rank, no ambiguity. An element will be of rank bounded by R if it can be written as a sum of R term, R elementary tensor product like this. In terms of functions, a bivariate function will be the sum of R product of univariate function like this. For higher order tensors, there are different notions of rank, and so it's a little bit more complicated. The basic notion of rank, quite natural, is the canonical rank, where the rank of a function will be bounded by R if it can be written as a sum of R elementary tensor product of function. Or in terms of multivariate function, it will be a sum of R product of univariate function like this. So it's a notion of canonical rank, but we have other definition of rank, and I will come later on the good properties of this new notion of rank. New, not so new when you see the slide, but numerical methods based on this new notion of rank are quite recent, in fact. So here you can very naturally define what we call the alpha rank, alpha being a subset of dimension. Okay, you have D dimension, you take alpha like this, like here, equal to 1, 2. You isolate the dimension 1, 2, and you see your tensor space as a tensor product of the space V alpha, which is itself a tensor product of V1 and V2, and the complementary space here, okay? So here you look at your tensor as a two-order tensor, and you have a unique notion of rank. The rank alpha will be bounded by R alpha if V can be written as a sum of R alpha functions, elementary tensor products, with here functions of the variable X alpha, X1, X2, and the other functions here are functions of X3, X4, okay? So here you have the notion of alpha rank associated to a subset of dimension. And here I start with my subspace point of view, and in fact tell you that there is a connection, a relation between this and the notion of what we call the minimal subspaces. The minimal subspace associated to a subset of dimension alpha for an element V is the smallest subspace in the space V alpha, such that the element can be written in the tensor product of this space, called the minimal subspace, tensor product with this. Okay? So it's the smallest, I would say, in terms of functions, it's the smallest subspace of function of the variable x alpha, such that V lives in this tensor product space. And the rank alpha of an element is nothing but the dimension of this minimal subspace. And I will come later, it's an important notion, this, which allows you to understand the nice properties of this notion of rank, and that will provide good topological and geometrical properties to the low-rank approximation subset. I will come to this later. So here I introduced a subset of dimension, but you can say, okay, I want to define a notion of rank for the dimension 1, 2, but maybe for the dimension 3, etc. So you have a combinatorial problem here for the definition of the rank. And a basic definition of rank, in fact, it's called the multilinear rank or Tucker rank. It's a tuple which associates a rank with each dimension. You will associate, you will bound the rank of your element with respect to the first dimension, the second, etc. Okay? And so an element with Tucker rank bounded by this tuple will be an element that can be written like this, a multiple sum like this of tensor product of univariate function like this. Okay, so here in this representation you see, so it's a nice representation from the numerical point of view, but you have still an issue because here this object is a multi-array, okay, called the core tensor, whose storage, in fact, storage complexity grows exponentially with the dimension still. And so there are other notions of ranks that have been introduced based on notions of trees. So you start with a tree of dimension like this. Dimension 1, 4 are split into 1, 2, and 3, 4. And then again 1, 2 split it into 1, 2, 3, 4. Okay? And you will associate with, associated with this tree a notion of rank with each node of the tree. And you will say that the rank, the T rank, where T is a tree, of an element is a tuple of integers that gives you the ranks, the different ranks associated with the different nodes. Okay? And then I will show you that I will give you some results that tells you that this kind of structure, okay, gives you quite nice topological and geometrical properties for the low-rank structures. And okay, so here I have introduced several notions of rank. And in fact, these different notions of rank lead to different, what we call tensor formats, okay? Subset of elements with a bounded rank. But of course, I have to define the rank in order to define my subset here. But a nice thing is that this subset of approximation have a small dimension. Small in the sense that typically they will have a dimension that grows only linearly with the dimension. And it is a case of tree-based formats that I have presented before. Okay, so a number of parameters that grows only linearly with the dimension. That means that if you are able to find an approximation of your function in such a subset with a fixed rank, you have broken the curse of dimensionality. Okay, you have only a complexity growing linearly with the dimension d. And in practice, what we observed, but we still need more quantitative results on this, is that we observe good approximation properties for this kind of approximation for a large class of applications of interest. No, yes, that's it. Not for Tucker. In fact, in this formula, the S that you see here is the maximal connectivity of a node in the tree. And for the Tucker subset here, it's D. Okay. So here you have broken this S. Typically for a binary tree, the S will be 3. It's the connectivity of a node. Okay, it's 1, 2, and the parent here, 3. Okay. Okay. So here, a result about the approximation, best approximation problem in this subset. You may ask, because this subset I have introduced here, it's not a linear space. It's neither a convex set. So you may ask, do we have best approximation results in this kind of strange manifold? Okay. So the answer is yes. For tree-based subset, so I mean, if you have the subset defined with respect to a tree, you have this positive results on best approximation problems, but you need to specify some topological properties. More precisely, in the tree, you have to associate a topology with each of the tensor spaces you have introduced here. V1, 2, V3, 4, etc. You have to, and that's why I said that in fact the basic definition of a tensor space, which is an algebraic space that you complete with a norm, it's not enough precise. Okay, you have to specify in this completion what is the structure you have given, the topological structure you have given all along the tree of dimensions. And if you introduce suitable assumptions, then you can prove that the rank, the function that associate to an element its rank, it's a weakly lower semi-continuous function, so that the subset I have defined by function with a rank bounded by some tuple is a weakly closed subset. And so if you are in reflexive Banach spaces, then you have the existence of best approximations. And in fact, this theorem directly applies for LP spaces that satisfy these assumptions. And what you can prove also is that for Sobolev spaces, Sobolev tensor spaces, you also can apply not directly this theorem, but indirectly by seeing your Sobolev space as an intersection of tensor Banach spaces. So I don't go into the detail of this, but there are positive results for approximation in Lebesgue spaces and Sobolev spaces. Just a word about algorithm to compute best approximation. In fact, there is no guaranteed algorithm to obtain best approximation in these subsets. They are not linear spaces, neither convex sets. So you have no guarantee to obtain the global optimum. But you have algorithms that provide you a stationary point of the functional. How is it far from the best approximation? We don't know, actually. There are no algorithm available for the moment. But in a very particular situation, where you are in a Hilbert setting, when you have Hilbert spaces, and the norm on your space is a very particular norm, which is the induced norm, the induced canonical norm on your tensor space, then you have algorithms that provide quasi-optimal approximation. You are able to, based on basically on higher order versions of the SVD, you are able to construct an approximation that is up to a constant, the optimal approximation in your subset. And this constant grows with the dimension, but not too fast, you see? Square root of d. So you have practical algorithm in order to compute. In a particular situation, I emphasize on this, when you manipulate here the norm, which is the induced canonical norm. And just to come to the previous notions, here in Sobolev spaces, you do not manipulate this norm. It's not the induced norm. Okay, the induced norm in Sobolev spaces maybe would be the H1 mix norm. Okay, so H1 is not a norm that allows such algorithm to be applied. Okay, so you have an issue for computing these best approximations. Just a slide also on the nice geometrical property for this subset. In fact, what you can show is that the set of tensors with a bounded rank R can be seen as a union of subset of fixed rank. Okay, you have a kind of stratification of your set here, which is a union over all S lower than R of this subset of fixed rank, and this subset of fixed rank can be proved to be analytic Banach manifolds. And even more, if you have the assumption I have mentioned previously, on the topological structure on your tree-based tensor format here, then under the same assumptions, you have that it is an embedded submanifold. Okay, so these are very nice geometrical properties. And there are many interesting consequences. Then, for example, you can devise optimization algorithm in this these manifolds, even using gradient of your functions, okay, because you are able to compute the tangent manifold to this embedded submanifold. And also there are interesting applications for dynamical systems where you are able to define reduced dynamical system projected in this submanifolds. Okay, and it allows you, for example, to extend the notion of the Dirac-Frenkel theory to this tensor framework. Okay, so now I have mentioned the structure, the Lowrank structure. The question is, you have an equation. How do you approximate the solution of this equation using these formats of approximation? First, you have to have the rank structure in your equation. So typically, you will have an operator equation like this with an operator given by a sum of elementary tensor products of operators like this. And the same for the right-hand side. So if you are, examples for this are quite classical. For the Laplace operator can be seen as a rank D tensor like this, which is a sum of D operators. Here you see you have only the differentiation with respect to the first variable and then the second, etc. So this Laplace operator has a tensor structure with a finite rank. Also for parameter-dependent operators, and it's quite well known, this kind of decomposition for reduced basis techniques, for example, where you have an affine decomposition of your parameter-dependent operator. A of the variables can be written as a sum of deterministic operators times functions, real-valued function of your parameters. And in fact, this can be interpreted in tensor format like this as a sum of elementary tensor product of operators like this. Okay, and here you live in the tensor product of a given Hilbert or Banach space, tensor product with the LP space. For higher dimensional problems, the same. If you have your operators that can be written as a sum of product of deterministic operators times univariate function like this, you have a tensor interpretation of these parameter-dependent operators, and you have the nice structures that allows you to apply the method I will present just after. So first, the first class of techniques to approximate the solution of an equation, it's to use iterative solver, your favorite iterative solvers. You have, for example, here an iteration of an algorithm that can be Richardson, conjugate writing methods, what you like for your equation, and what you know it's a convergent algorithm, okay? And then here, because you live in this very high-dimensional tensor space, you will systematically introduce low-rank approximations of the different iterates of your algorithm. If you have the nice topological structure I have introduced before, I mean, if you work in a Hilbert setting with the induced norms, then the truncation, the approximation in low-rank manifold at each iteration can be performed using very efficient SVD type algorithm. Okay, the algorithm I have mentioned previously. If you don't have this induced norm structure, then you will also have the issue of approximating at each step in this low-rank manifold with respect to more general norms. But it's a quite natural way to approximate solution of equation. You have an iterative solver, and you perturb this iterative solver by introducing low-rank approximation at each step of the algorithm. Another strategy is to directly try to approximate the solution in these subsets. But of course, since you don't have the solution, you will have to replace this minimization of the distance by some minimization of a certain criterion. Okay, a certain distance to the solution. If you have a natural minimization problem in your problem, there is a natural way to define this distance between the solution and the V. If you don't have these natural optimization problems in your problem, you can rely on a residual and try to minimize the residual norm. Okay, so here you have the issue how to measure the residual. So it's closely related to the notion of preconditioning, in order to have a measure of the residual which is close to what you want to optimize. But still, it's a quite natural way to define a distance between you and your approximation. And also in the context of stochastic or parametric equations, you have also a natural way to define a distance, or a pseudo-distance, I would say, based on samplings of your solution. You will define a distance based on samples of the solution that can be computed by sampling, by solving your model for different samples of the solution. So now, the subspace point of view, which is quite interesting to see the connection between this Lowrank approximation and the notion of model reduction. And to show you, to convince you, I will mainly focus here on the two other cases because it allows you to understand the main ideas in this subspace point of view. So I start with another two tensors living in tensor product of V and S. So have in mind the problem in for stochastic or parametric equations. That means here, have in mind in this presentation, the V typically will be for the diffusion equation H10, for example, on a given domain. And the S will be LP, or let's say L2. L2 function defined on the parameter space equipped with a probability measure. Okay? And so, here there is a unique notion of rank. An element will be of rank bounded by M if it can be written as a sum like this. And in this context, see the function W as a function of your parameters. And here I write that it can be written like this. Elements of your space V times function of the parameters. Okay? So have this context in mind. So you can define the set of rank M tensors, like the set of elements that have a bounded rank M. And then if you consider a tensor, U, that you want to approximate, that the best rank M approximation is something written like this, and you will define it as the approximation that minimizes the distance to the solution in this subset Rm. And you see that it's a way to define optimal vectors. The optimal approximation like this defines M vectors in the space V and M vectors in the space S, okay, that better approximate the tensor U. Okay? So now you can adopt a subspace point of view and reparameterize your subset of rank M element, in fact, as the set of elements that are elements of a tensor product space, a tensor product of an M-dimensional space, tensor product with another M-dimensional space. So in fact, this manifold here is parameterized by M-dimensional spaces. Okay? And so the optimization problem in this manifold is nothing but an optimization problem on the M-dimensional subspaces. Okay? So you can see it as an optimization problem on Grassmann manifolds, in fact. When you try to find the optimal approximation of U in Rm, it's a problem of finding optimal spaces. So here is a connection with optimal subspace-based model reduction. If you're able to find UM, in fact, you have found the optimal reduced spaces to approximate your function. There is a particular case where things are well understood. The case where you are in a Hilbert setting with a norm which is the induced norm, induced canonical norm. In this situation, you know that your tensor can be identified with a compact operator from one space to the other. And you have the singular value decomposition. You know that your tensor can be written as an infinite sum like this of tensor product of orthogonal elements. Okay? And you know that with this particular norm, the best rank M approximation is nothing but the truncation of this series after M terms. Okay? So it's a very particular situation where the best M term approximation can be obtained by truncating a series. Okay? And so you have a notion of decomposition here, really. The optimal M term, M plus 1 term, is just obtained by adding the following terms in the series. And also, the optimal spaces that are defined when you compute this best approximation are nested. It's an interesting property which gives you a kind of constructive algorithm in order to approximate, to better and better approximate your function. Now, in the more general setting, where you introduce these distances to the solution based on the residual of your equation, for example, you lose this structure I have presented. Still, you can define the best approximation with respect to this distance. It will define optimal spaces of dimension m also, so it's also related to an optimal model reduction, but usually the spaces, optimal spaces, will not be nested. So, is it a problem or not? From an adaptive point of view, it may be a difficulty. I mean, in order to obtain a rank m+1 approximation, the optimal one, then you cannot really use the rank m approximation. Not really, but in fact, in some situations, yes. And I will present you after constructive algorithms that try to be suboptimal and constructive. And in some way, you have quasi-optimality results still. Okay? But in this general situation, a priori, you have no notion of decomposition. And a particular case of interest, so it's this situation where you have a distance to the solution which is equivalent to the distance, the LP distance in a Bochner space. Then you have a well-understood situation where for p equal to infinite, in fact, the best approximation in the subset of rank m element, you can recast this problem as an optimization problem on the set of m-dimensional spaces, times the distance between you and its projection on this subspace, which is here with respect to this infinite norm, the supremum over all parameters of the distance between uxc and the projection of uxc on the space Vm. It's exactly this, the best approximation in Rm. It's equal to this. And here maybe you recognize what is called the Kolmogorov M-width of the set of solutions. If you consider all possible solutions of your problem, that means the set of elements of V that is composed by U of C spanning the subset of parameter C. It's called the solution manifold. And this error, best approximation error, is what we call the Kolmogorov M-width of this subset. That measures in some way how well the set of solutions can be approximated by a m-dimensional space. Okay? In the p different to infinity case, then you have some also an interpretation in terms of a width of this solution manifold, but here, in fact, the notion of linear width you obtain is measure dependent. So I would say it's more suitable for, in the context of uncertainty quantification, to take into account the measure on your parameter set in order to characterize the approximability properties of this subset of solutions. Okay. So now, I mentioned that this optimal rank M approximation is related to optimal model reduction with subspaces which are not nested. So you have no constructive algorithms that arise in this general situation. So what you may ask is there algorithms that recover this notion of constructivity, okay, or adaptivity? And in fact, there are algorithms that have been proposed that try to be constructive in this approximation. These are reduced basis methods in the L-infinite case that tries to construct nested suboptimal but nested sequences of subspaces in order to approximate the set of solutions. Proper generalized decompositions, I would say the main application of this technique are in the Hilbert setting, L2 setting. And, but they are based on the same principle. And here I will show you two basic algorithms that are called PGD algorithms that are different variants. First, the first algorithm that adopt a greedy construction in the approximation. So very easy. To construct a rank M approximation, you will build one by one the different rank 1 terms in your expansion. Okay, so once you have a rank m-1 approximation, you try to find the optimal correction written like this as a tensor product of an element in V times an element in S by minimizing successively this distance you have defined. By construction, you have a notion of decomposition. And by construction, the subspaces you have defined here are nested. But in fact, you see that this construction does not really exploit the structure, the tensor structure of your problem. In fact, it can be interpreted here as an m-term approximation each term living in a certain manifold, which is a rank 1 manifold, but it may be something else, and which is constructed by a greedy algorithm. So there are very general results about this kind of greedy algorithm in other situations that can be applied to analyze the properties of this algorithm. But here what you can do is exploit the tensor structure of your problem and adopt another type of greedy constructions that are greedy in the construction of the subspaces. So here you look at your object and see its tensor structure and see the thing like this. You will try, so in black here you have the definition of the best approximation with a rank m element, which I mentioned is a minimization problem over the set of m-dimensional spaces. The optimal spaces are not nested. What you can introduce here is a suboptimal construction that will incorporate, again, this notion, this nestedness property. You can do it, okay? By simply optimizing, so it's a suboptimal construction that imposes the nestedness property on your spaces, okay? And in a Hilbert setting, in fact, you can prove that, in fact, it is a quite nice manifold here, and you can introduce algorithm to compute optimal approximation in this. So usually we use an alternated direction algorithm in order to compute approximation in this. So I don't go into the detail, but here you have another construction, a little bit less suboptimal, where in fact the nestedness property, you only impose it on the subspace V. And with this type of construction, we are very close from the construction used in reduced basis method, if you know this type of method, that try to introduce nested subspaces with an additional property that they can be spanned by samples of the solution, snapshot of the solution. So here you don't have this constraint, just the nestedness property in the construction. So you have other algorithms that we have introduced that are also suboptimal, that try to be more efficient in some way. So the interest of this adaptive algorithm, I have to mention it, because optimization in the set of rank m element is feasible. It's a manifold. You can devise optimization algorithm in it. Okay, but when you deal with very complex numerical models, then trying to find simultaneously m functions here living in the space V, and V can be a finite element space of dimension 1 billion. Okay, then addressing this optimization problem with m equal 10, 100, etc. It leads to very, very complex approximation problems, okay? A very, very dramatic complexity. So these greedy construction in the subspace have the nice property of being constructive in the construction of this set of functions, and requires, in fact, at each step of the algorithm here, only the solution of problems of the complexity V. Okay, and not V to the power m. So it's an interesting property of this kind of greedy constructions. And in terms of another language here to say things, is that these algorithms are algorithms for the greedy construction of a reduced basis. Okay, the reduced basis that span the spaces VM that are constructed by these algorithms, that are suboptimal subspaces, but still quite good subspaces. Here I have the illustration of the complex test case. Here you have several random variables. So here I mentioned the variability and the diffusion coefficient in your layers, but also you have uncertainties in the benchmarks that were given on the boundaries, on the boundary condition of this problem. Well, here you have a problem with 10 stochastic dimensions, 10 random variables to describe the uncertainty. And here these are the spatial functions that are constructed by the algorithm. So you have several iterations to compute this function, but the number of computation of complexity V, so finite element approximations here, is of the order of 8 in order to compute these 8 functions. Okay? And when you look at the errors here, you see that for this problem, with respect to the rank, so the dimension of your reduced space, the error goes quite fast to 0. Okay, you reach an error of 10 to the minus 6 with a reduced space of dimension 20 here, and you see the difference between the blue curve, which is a greedy construction of the approximation by adding rank 1 corrections to your approximation, and the greedy construction on the subspace where you gain 2 orders of magnitude for the same complexity, okay, in your computation. Yeah, but here in the L2 setting. So it will be the L2 counterpart of the reduced basis algorithm, which is constructive in the subspace. Okay, the blue one, it's this algorithm where you impose the nestedness property of the subspaces. The black one, sorry, the black one, and the blue one is this algorithm that never goes back to the past and construct one by one these tensor elementary tensor products. Yes, but here I ordered 2. So the main application of these algorithms is for parameter-dependent problems, where my focus is to construct a deterministic reduced basis here. Okay, so it's yeah, I would say the L2 counterpart of reduced basis algorithms constructed by reduced basis greedy algorithm, I would say. Okay, so just a slide to give you the results we have on these algorithms. If you are in the very particular setting of a Hilbert space with the induced norms, where you know that there exists a singular value decomposition, that all the algorithm I have presented gives you exactly the best rank M approximation. In this degenerate case, the algorithm provides the best rank M approximation. If you are in a more general case, for example, if you try to minimize the residual of your equation, even if your residual is an equivalent, a distance equivalent to the norm, to the natural norm of your problem, for example, in the LP case, the Bochner's case with P different to 2 for this distance, then you have convergence results. You are able to prove that the algorithm I have presented converge. But what about quasi-optimality of this construction? I don't know. There are results in L-infinite case with greedy type algorithm for reduced basis. In this situation, LP case, and even in the L2 case, okay, even in a simple Hilbert setting, we don't have results, only experiments. That tells us that, in fact, it seems that we have a quasi-optimality in the sense that this algorithm provides something which is very close to the best approximation in the subspace, but we would like to have, like for reduced basis construction, here an inequality with a certain constant that is controlled. Okay, so there is an open question on here, how to compare this approximation error with the best thing you can do. And I will finish by showing that these ideas can be extended to higher dimensional situations. And in fact, it can be extended to these higher dimensional situations when you adopt approximation formats that are based on subspaces. And it is the case of the Tucker approximation, of the tree-based approximation, not the canonical approximation. Okay, the notion of canonical rank do not enter this framework. Let's start with a simple case of the Tucker subset, which are elements with a rank mu bounded by R mu for all dimension mu. In fact, this subset can be seen as a set of elements that lives in the tensor product of R mu dimensional spaces. You have a reparametrization of this subset also in terms of low dimensional spaces. So the best approximation in this subset is nothing but an optimization problem over a set of R mu dimensional spaces. So you have a direct translation of what I presented before to this higher order setting. Okay? So in some way, optimizing a function in this element is equivalent to finding reduced approximation spaces to approximate your function. In terms of multivariate function, you try to find a R1 dimensional space of univariate function of the first variable x1, a subspace of function of the second variable, a subspace of dimension R2, etc., etc. Okay? So now, based on the same principle as before, you can try to construct in a greedy way these subspaces by imposing this nestedness property, because you lose it in the general framework, but you can impose it in the construction and be greedy in the construction of all these spaces here in this parametrization. Okay. You can also rely on a suboptimal greedy construction. For example, you can try to find a best rank 1 correction as a product of univariate function like this, and enrich your spaces by the different coordinates here, the different univariate function. You enrich the spaces. You do not use this correction as a correction of your approximation, but just as a way to enrich your spaces in each dimension, and then you project in the tensor product space. Okay, and here I have a simple illustration of this, of the nice property of this kind of algorithm on a benchmark. In fact, very simple situation where almost all algorithm works well, okay? But still, it's an illustration of the performance of this greedy construction of subspaces. So it's a Poisson equation, where here you have a natural distance associated with your operator, which is in fact the H1 norm. When you apply this algorithm, here I have an illustration of the error with respect to the rank. Here in this plot, you have different notions of rank. The blue curve is a canonical rank. Here the x-axis is a canonical rank for the blue curve, which is constructed by a greedy algorithm. You successively find best rank 1 correction of your function. And you see that in this problem, the convergence, it's not very good for this type of greedy constructions. You can try to be optimal in the set of rank R canonical functions by optimizing in the manifold of element of rank R, and it performs a little bit better. And here, what you have is a construction based on the subspaces. And you see that we obtain an exponential convergence of this type of construction. So here at step 10, you have an error 10 to the minus 6. What does it mean? That means that you have found a 10-dimensional space of functions of the first variable, a 10-dimensional space of functions of the second, etc., such that the projection of your function in the tensor product of these univariate spaces has an error 10 to the minus 6. Okay? So this greedy construction of spaces appears to be, in this situation, really optimal, quasi-optimal, because the blue curve that you see here is really the optimal that we were able to compute. We are not guaranteed that it is really the optimal, but we try to find the optimal spaces of the same dimension. And you see that the greedy construction, which is red, it's almost optimal. Okay? So you have this quasi-optimality which is observed here, and I come back to the open questions in the previous section. Okay? There is an open problem here to prove, in fact, if this quasi-optimality property of this kind of subspace-based algorithm. And last comment, so here I wanted to mention the work of Virginie Erlaché and Loïc Giraldi on the application of these concepts to problem in quantum chemistry, where you have to solve eigenvalue problem. In fact, this eigenvalue problem, where you try to find the minimal eigenvalue of this problem, can be recasted as an optimization problem, where you try to minimize the Rayleigh quotient. Okay? And so you can apply the machinery I have presented before, and have successive optimization of this Rayleigh quotient on these tensor spaces, where you introduce this nestedness property of the subspaces you are trying to find, etc., etc., and you obtain, in fact, very, very fast convergence of this type of construction for whether high-dimensional problem. Here it's a problem in dimension 20, where you see that greedy algorithms are very slow compared to this construction based on subspaces. So it appears to be quite efficient in this situation. I skip very fast this. It's an anisotropic construction. So here I have presented the Tucker format. I enrich the spaces in each dimension. So of course the issue is that in order to break the curse of dimensionality, you have to use in some way anisotropy of the function, and so introduce anisotropic versions of these constructive algorithms that will enrich more a subspace, for example, functions of the first variable, more than the function of the second, etc., etc. So you can propose a constructive algorithm like this that exploit anisotropy. And I skip here and arrive to this slide of conclusion, where I would say that, okay, these structures appear to be quite efficient in practice. It appears to have, you have many problems with solution have this kind of low-rank structures. But you see that in the definition of rank, I have plenty of choices. And in this tree-based format, it is closely related to the choice of a tree. So it is really an issue, actually, how to design a tree, how to find an optimal tree for the representation of a function. Okay. Also, I would mention a rather important issue is that you see that the algorithm I have presented exploit the tensor structure of your equations. If you have very complex models, recasting a problem in this framework, it's quite a heavy task, okay? And so there is also a challenge to devise some, I would say, non-intrusive implementation of this kind of strategy that will allow you to find, to approximate your equation in a tensor framework, okay, in a tensor format, in order to have the applicability of this kind of algorithms. And I trust in sample-based constructions in order to, in the context of stochastic parametric analysis, sample-based construction of low-rank approximations that try to do the job I have presented in a quite non-intrusive way. That means using the deterministic codes you have for your favorite applications. Okay. So, and I stop there. Thank you.
Thank you very much, Anthony, for this talk, which I found very fascinating, actually. And we have a little bit of time, maybe for one or two quick questions. Jérôme?
You said that the algorithm that you find the suboptimal algorithm do not work for the classical H1 norm. Sorry. They do not work for the classical H1 norm. You need to have an induced norm in a Hilbert case.
Okay. No, I mentioned that in the case of induced norms, so if you work in H1 max, then you have available algorithm based on SVD.
What is H1 max? That's my question.
H1 max is in a tensor language. H1 max is this. I don't know if you see it's large enough. H1 max is a tensor space, which is nothing but the completion of your algebraic space, which is a tensor product of H1 space, with respect to this norm, the H1 max norm.
What is the H1 max?
H1 max norm is where you have in the norm you have all mixed derivative. Okay. For H1, but let's say H1 you will have only the derivative like this, and for H1 mix you have all mixed derivatives.
So it's nearly an H2 space. It's between H1 and H2. Secondary.
Yes, that's it. Okay. Oh, no. H1 mix. You have no inclusion. Indeed, you are. In fact, you are very regular in H1 mix spaces. You have no inclusion. H1 included in H1 is included in H1 mix, but you cannot include it in H2. In H2, you have not all these mixed derivative of higher order.
It's like the P and Q polynomials for finite element analysis. You have one derivative of order D here, right?
Yeah, and you cannot embed the P1 in the Q1 in the P2.
Yeah.
In higher dimension, maybe in 2D it's okay, but not in higher dimension.
Any other question? I wanted to ask you a very general question, actually. When you have time-dependent PDEs, which have some also, I mean, you have D, you have time, and you will have Xi.
Yeah.
Is there like some issue on maybe regrouping time with the parameter?
I have only experiments on this, numerical experiments. I don't know the good strategy, but what you can do, you can apply the algorithm I have presented that are constructive in the subspaces for parameter-dependent problem with a V, which is let's say this.
Yeah.
Okay? You can apply this, or if you want the good functional framework, you have to intersect this with the space H1. For parametric problem, you will have this. Okay? And you can apply the strategy I have presented that are constructive in the construction of reduced basis in this. This will be reduced basis of space-time functions. Mm-hmm. And it works quite well. In practice, we apply this kind of algorithm. So you will have a succession of parabolic problems to solve in order to find the reduced basis in this. But also you can exploit other tensor structures and see also the tensor structure here, okay, of this space. And then so this is an issue. How do you decompose the function of the space, the time, and the variables? This is what I presented in this talk. But you can also have other type of decomposition that are pertinent from the functional framework, but it's more related to the structure of your solution. So it's an interesting question for a given problem. What is preferable? How can you obtain low dimensional in your problem? Does it exist a low dimensional basis of function like this for approximating U? Maybe in some situation it's not the case, but maybe using this structure you will find a low dimensional space here. So it depends on the problem, and we really need some quantitative results that connect this kind of structure with the problem you have.
Is it related to the choice of the tree also?
Yes, in some way, because here you see you have three spaces. Okay, let's call it Vx, Vt, Vxc. Okay, so I would say you have a choice here, and indeed it is related to the notion of tree, because in this representation I impose the rank xt to be lower than m.
Yes.
It's a choice of tree, but I can choose another tree. So indeed, this kind of choice is related to the notion of tree.
Yes.
Yeah.
Okay, thank you very much for your talk.
Thank you.